Face recognition. We want to match faces in the images to one of the known subjects in the database. My dataset includes 11 classes of the publicly available dataset called Cassia Web Face. First, we create our environment and we through the following commands, and then we divide the data into train, validation, and test. Uh, For the overview of the face recognition project, in the first step, I am predicting a set of images in the validation and test dataset using pre-trained models of VGG16 and ResNet50 trained on VGG Phase 2 dataset. Then I explore ways to improve existing pre-trained models performance through feature extraction, transfer learning, and fine-tuning. In this step, I create 8 models and compare their accuracy and loss. Then I want to explore what happens if we want to add another person to our database, or what if we want to classify an image that does not belong to someone in our database, or what if our database only includes one image per person. Then I'm using a pre-trained model created by Google called FaceNet that's pre-trained on MS Celeb 1 million data set. Before going through the first step, we need to prepare our images by extracting the part of the image that is the face. For that reason, I'm using the MTCNN package. And if there is more than one face in an image, I use the one with greater area. Using VGG Phase 2 dataset, and VGG16 and ResNet50 architectures on my own dataset, the result shows that although VGG Phase 2 dataset does include all the 11 categories of my subjects, the VGG16 identifies 3 of them and ResNet50 identifies none of them. Then in the next step, I extract features and labels in trained, validation, and test folders by predicting from their convolutional base, and then feed them into a model that I create. In this step, we are using dropouts and regularizers for regularization and avoiding overfitting. Here are the results. The top results are for VGG16 and below for ResNet50. We see that in both cases, validation and training accuracy remain constant. In transfer learning, we are building a model on top of the convolutional base of VGG16 and ResNet50. We freeze the parameters of the convolutional base and train the parameters of the added hidden dense layer and classifier layer. In this step, I'm using image augmentation and regularization as well. We see that VGG16, when added one dense hidden layer or added 2 dense hidden layers, the accuracy is completely the same. Whereas for ResNet50, adding 2 hidden dense layer improved the accuracy from 76% to 94%. Then the next improvement is fine-tuning, where we build a model on top of the convolutional base of VGG16 and ResNet50, and we only unfreeze the parameters of the all layers in the last convolutional block. This is something you can choose. You can try to train more layers or less. Then the remaining layers in the convolutional base are frozen. Then the parameters in the last convolutional block and added dense layer are retrained. The results show that accuracy of both VGG16 and ResNet models improved in fine-tuning, and the greater improvement is for ResNet50. Here is an illustration of a candidate set of test images from transfer learning and fine-tuning models, which are all correctly classified. Here are some of the illustrations from images that include more than one face in them and have less clear image. And also it does include faces that do not belong in the database. And our models predict these people as one of the 11 subjects, although they are not in the database. Therefore, in order to be able to classify them as not in database, or easily being able to add a new person to our database, I want to explore the FaceNet model developed by Google. In this model, instead of learning a mapping from images to classes, we learn a mapping from images to embeddings. Therefore, for each image in the database, we create an embedding, and when we have a candidate image to predict, we compare the embedding of the candidate image with the embeddings in the database, and use a distance function for that reason. Here is the predictions from the FaceNet, the model that repurposes the FaceNet pre-trained model. We have correctly identified all of the faces in images and correctly identified those not in database, even for the pictures with very low quality image. Lessons learned. We see that repurposing models significantly improve the accuracy of the models. Also, the accuracy of the models strongly depend on the underlying network architecture and not necessarily the number of layers. The performance of repurposed models also strongly depend on the number of images that they are pre-trained on and the learning algorithm that they have. In the fine-tuning section, we saw that fine-tuning improved validation accuracy for more than transfer learning for both models. Models using VGG16's convolutional base responded better than ResNet 50 in transfer learning. But when 2 layers were added, ResNet 50 compensated to the same accuracy. Also, using ResNet 50's convolutional base responded better to VGG16 in fine-tuning.